Yeah, guys, spatial autocorrelation is the topic, and we are going to move away from it very quickly. But we need to understand that Tobler, Ayoke, who is actually known to be the the father of geography, came up with a theory, and the theory was this, or he said that everything is related to everything else, but near things are more related than distant things. Is that okay? So what does that mean? I said that you could just check. I think I've already talked about this one, haven't I? Okay, guys, can you confirm that I've already talked about this? Have I? I think before we went in a break. Okay, so now spatial autocorrelation itself is a statistic. Okay, and the statistic measure and analyze the degree of dependency among observation geographic space. And I was saying that what does this English mean? This English actually means that for everything that you see, the relationship may be to a certain, you can quantify somehow, and of course statistically, okay, as opposed to numerically. Are you okay? And measure how related. So I can be more related to my mom or my dad than you. Are you with me? It doesn't mean I'm not related to you, because obviously I see everybody in my department, you know what I'm saying, to be like a son to me. Are you with me? But then if I have my own biological son, and obviously the relationship is different, there's a slight, are you okay? There's a degree, are you okay? So we're talking about a measure, okay, of the degree of dependency. So how much am I dependent on? So that can be estimated using the autocorrelation, spatial autocorrelation measure. Are you okay? And I said that when you look at the existence of gold in quartz veins, that is what most geologists actually know. They know that if we find quartz veins, then very likely there are somewhat there's gold in there. Are you okay? So why don't I go looking for quartz veins, and then that could lead me to where the gold is and stuff like that. Okay, so there is a certain level of dependence between things, everything that we see around us. But then we can measure. Okay, so we can measure how much. So when you look at this diagram here, we are actually having so many polygons. Is that okay? And then these polygons have certain values or observations in there, and then we can work out the spatial autocorrelation based on where they are. Remember that spatial autocorrelation has to make use of space. So a correlation within space, a correlation within space. So we all know correlation. All right, okay. So correlation between different variables is mathematical. Are you okay? But then we can actually look at spatial autocorrelation in terms of how your location affects your dependence. Are you okay? How so you can determine me by just knowing where you are. Knowing that you are here means that I am, I'm affected so much. We can look at the chameleon, for example. The chameleon, anywhere it is, it changes to suit the environment. Are you okay? So there's that dependency on the colors around the chameleon. We can look at it that way. But anyway, it boils down to a formula, a simple formula that will be used. Are you okay? We have so many ways of measuring spatial autocorrelation. We have what we call the Moran's I, and then we have the GIS C. Okay, so these allow us to measure spatial autocorrelation, and they are very classic. Are you okay? All right. Now they require the measuring. Okay, they require measuring a spatial weight matrix. So the weights that we talked about earlier on, okay, can be applied as well. And the weights reflect the intensity of the geographic relationship between the observations and the neighborhood. Okay, so if I wanted to find the level of dependency, if I wanted to measure spatial autocorrelation, then I'll need a weight, a spatial weight, and that spatial weight has to reflect the intensity of the geographic relationship between the objects. Is okay? It can be distance. Distance has been used as one of the weights, for measuring some of these things, but yeah, we need to know that the weight has to be relevant. Are you okay? Classic spatial autocorrelation statistics compare the spatial weights to the covariance relationship at pairs of locations. So what we are doing is that we are simply measuring a certain relationship between pairs of locations. Okay, so we can have so many locations, and then we try to just find out what's the relationship between X, I, J, and then, you know what I'm saying, the next one. Okay, if you change I and J, then what we're gonna find out. Spatial autocorrelation that is more positive than expected from random indicates the clustering of similar values across geographic space. So here, I'm sure Nana Bunsu, if you are listening to me, you realize that clustering is coming in here. Okay, and it's okay. It's okay. It's okay to have it here because obviously, if I'm dependent on you, are you okay? If there's a level of dependency between you and me, then it means we are somehow, are you okay, clustered. We are together. We are together. We're together. All right. So spatial autocorrelation obviously has got something to do with objects that are close and yet are related. Is that okay? All right. So we can talk about the random bits where events are not just we need to compare with a random IOK, random values. So the actual values that we have, observations that we've made, let's assume that if they were just random, what do we get? IOK. Now it says while significant negative spatial autocorrelation indicates that the neighboring values are more dissimilar than expected by chance. So you see random and chance is coming in here. So it's similar to the way we compute the nearest neighbor index. Okay, so something like the chessboard. When I don't know if you all seen the chessboard before, but the chessboard is a typical example of negative spatial autocorrelation. We have black separated with white, or drafts, dummy, what we call dummy in the local, language. Chess always has, or that draft has black, white, black, white, black, white. You see that you haven't, there's no relationship. Are you okay? But where you have a continuity of the colors, then obviously there's some sort of dependency. Morans I and Jerry C are global autocorrelation, okay? And they may vary significantly across geographic space. Are you okay? All right. So we talk about that variation within space, across space, it's also called heterogeneity. Is that okay? As opposed to homogeneity. Is that okay? So when you take the chessboard, then there is actually heterogeneity. There's no uniformity on the chessboard. It's just black, white, black, white. You can't see any trend. Are you okay? That okay? I can see, that I have a lot of things that are similar. Are you okay? They are dissimilar. Okay, so homogeneity and heterogeneity are concepts relating to the uniformity or lack thereof of a substance. I think I just talked about that. Okay, so our software, please, this software, you need to install it. I don't know if I've told you already, install CrimeStar software. So this is the second time we're talking about it. We'll be using it to generate statistics very soon. All right. So spatial autocorrelation in terms of the Morans I statistic, this is the formula that is used. Is that okay? So we need to understand how these things work. We end up calculating I. Okay, so this single value here is calculated. All right, and then this is how we do it. Is that okay? So you have a total number of observations. You have points, the S coordinates, okay, of the observations. All right, and then we can take one point, take the other point, okay, we compare them. So for example, when you write X subscript I, then we know that we are dealing with the I, coordinate, okay, then the Jth coordinate as well. And obviously that is the mean of observations, is that okay? And then we do a sum over the number of other points that we are actually visiting, is that okay? So Wij is the weight matrix between 2 points. It could be the distance between the 2 points, point I and then J. Is that okay? All right. So basically, if I have several points, so these are all points, okay, then obviously point 1, point 2, point 3. Maybe let me just leave it and go to the whiteboard. Where is the whiteboard? Okay. So if I have several points, is that okay? Then I can be moving from one point to the other. So I move from I all the way to N. Okay, so I to N. That is what we are looking at over there. When I write Xi, then I will be varying from 1 all the way to the last point. So this could be 1, 2, 3, 4, 5, 6. Are you okay? So as I change I, so the Xi you are seeing there represent all the points. We'll be visiting them as we go from 1 all the way to N. And then we can have J as well. That means the other point is okay. So when you have something like Sj, then obviously J can also, so we can have Wij to be W11. So we are referring to point number 1. Okay, you can have W12. That means that from point 1 to point 2, what is the weight okay associated with this? If you want to find the dependency or for this whole point, if you want to work out the spatial autocorrelation, the level of dependency among objects here, we'll have to consider all the points and how they relate to each other. Are you okay? So between point 1 and then point 2, we can have W15. Are you okay? So that these are typical values. Are you okay? And then this, like I said, Wij is a weight matrix that should reflect the intensity of the relationship between the points. So if maybe we can assume that the nearer points are to each other, then the more related. In that case, then distance becomes a weight. Okay. So we should be able to interpret a formula like this. Like I said, the S bar is the mean of the coordinates. So these are simply coordinates, and we work out an I. Remember that the I that we compute per the observation should be compared with the I computed per chance, and then we find out if it's actually there's a genuine relationship. Yeah, dependency is not based on chance, but real. So it's being repeated here again. Wij is a distance-based weight, which is the inverse distance between locations I and J. Is that okay? So there you go. The weighted Moran's I is similar to correlation coefficient. Okay, that's fine. And etc. We can also look at an example over here. So here, motor vehicle thefts, okay, in a certain county called Baltimore. It could have been anywhere. It could have been in Adenta municipality. And then Baltimore City by individual blocks. So we, like I said, we can make use of spatial units like blocks. Are you okay? And then 14,853 vehicle theft locations were analyzed. Is that okay? And then we have 13,101 census blocks that we want to actually use. So we are aggregating the incident locations to the zones. Are you okay? The aggregation is happening. And then the software calculated I to be this value here, 0.01, 2, etc. And the theoretical value of I is that. Are you okay? So that's based on chance. That's what we get. Now we test for significance using the normality assumption, and then we get a Z value. And then we applied statistics to find out if it's significant, the I that we got. Are you okay? All right. Now, by calculating the Z score, which I think all of you know it, the expected value, the actual Z value versus the standard deviation, all right, then we obtain a value of 125. And we are saying that it is significant. Okay, motor thefts are highly and positively spatially autocorrelated. Are you okay? So that is the way that it is done. You have to find the significance of it. You can calculate the I and realize that, you know, spatial autocorrelation is positive, but then it may not be, you know, significant. Okay, compare with the random. So that is what we are trying to do in this calculation. All right. So blocks with many incidents tend to be located close to blocks which also have many incidents. And conversely, are you okay? All right. So that is what the interpretation is. Blocks with few or no incidents tend to be located close to blocks which also have few or no incidents. I think this one is not, you know, rocket science. We can understand it. The same thing is done with the Moran's I. The formula is slightly different. We don't have just n, we have n-1. Okay, and then also this one is, the numerator is quite simplified in this case. All right, and then so there's a slight difference in the equation. If I don't know if you can actually chew this in your head, but obviously if you are doing traditional exam, then you should be worried about that. If you are doing online exam, you shouldn't be worried about that at all. There's a weight. Are you okay? The weight value is there. We have the S coordinate of the ith observation, S coordinate of the jth observation. Are you with me? And then we can just keep going on and on and on and on and on. It's okay. So, but spatial autocorrelation, the idea is to measure if events are more related. With the GIS, so I told you we have two formulas. We have the Moran's I calculation or formula. Then we have the GIS statistic. Okay, they are just formulas that are used to compute a single value. All right. So with the C, the values vary between 0 and 2. Values less than 1, that is line between 0 and 1, typically indicate positive. Okay, and anything greater than 1 is negative. That is tricky, isn't it? All right, so greater than 1 rather is negative, but that is the way the formula has been designed. So you just go by that. Okay, any question on spatial autocorrelation? Why do you think we are doing spatial autocorrelation? Why do you think it's relevant? How can it be used? What kind of data sets is required? Are you okay to do your spatial autocorrelation? These are the questions that you should be asking. Spatial dependency between observations. What is that? What does that mean? If one thing is dependent on the other, you know, what does it reveal to you? The next topic is on exploratory spatial data analysis. I think this one is basically data analysis, quite statistical, but we introduce an element of the map in it. So when you look at the diagram on the board, then you see that we have a map over here, but on the right hand side we have a graphical output, okay, that actually try to relate to what we have on the left hand side. Here we have a certain graph over here, okay, that a box plot. This is actually called a box plot. Yes, this one here is a box plot. This is the map, okay, and then this is a scatter graph. All right, so we are bringing statistics and then mapping together, okay, geography, statistics together in what we call exploratory spatial data analysis. Exploratory spatial data analysis. So what is it? First, before you understand exploratory spatial data analysis, you need to understand what data analysis itself is about. Are you okay? So exploratory data analysis, the aim is to do what? The aim is of exploratory data analysis is to identify data properties for purposes of pattern detection in data. Okay, you may want to find out if there is a pattern in the data that you actually, you know, having in your hand. Hypothesis formulation is one of them. Okay, and then model assessments. Okay, in other words, goodness of fit, identifying data effects on model fit. In other words, you have a set of points and you want to find out, does it fit? For example, if you are trying to, if there's a linear relationship then you may want to fit a line to it and find out the gradients. I believe we all done something like that before. That is what data analysis is about. Exploratory data analysis is about. We should be able to find if there's a pattern. I think this is done a lot. Anybody who's done physics before know what I'm talking about. That, you know, you could do an experiment in which there's a formula that you want it to fit. So you know, that is what data analysis is all about. Okay. EDA is based on the use of graphical methods. So you need to make use of graphics. Okay, you plotting graphs, visual methods, you need to look at it. Okay, and numerical techniques, and they should be statistically robust. All right, and that means that they shouldn't be much affected by extreme values. Okay. EDA emphasizes on descriptive methods. Is that okay? Descriptive method rather than formal hypothesis testing. Okay, these are all statistics related stuff. So exploratory spatial data analysis, what is that about? Then we want to introduce a spatial, you know, dimension. Are you okay? And what are the additional techniques that we can use? We can actually make use of, you know, spatial patterns, you know, determining spatial patterns in that case. All right, formulating hypotheses based on geography of the data. So you can be measuring, say, the amount of, say, arsenic, you know, in the mining area. There's a lot of pollution from the activity. So if you were actually collecting data on that, then you can actually be, you know, assessing, you know, whether there's a pattern in that those values that you are measuring. Can you predict, etc.? Build a model that says that if you are 2 kilometers away, then there's so much arsenic that we will find, etc. So that there are spatial models that can be built. Is that okay? All right. But one of the things that is interesting about ESDA is our ability to do what we call the brushing. Okay, we can actually click on the map and then get to know the statistic. Okay, normally statistics don't look at the map, but is there a way to link the graphics and the visuals with the actual map? That is one of the objectives. Okay, so ESDA should be able to link numerical and graphical procedures with the map. Okay, exploratory spatial data analysis should be able to do that. All right, so data model for ESD, a set of data can be thought of as having general trends. Of course, I mean, we can always talk about average values of relation, local variations, etc. So if you do a graph, you know, you will appreciate what I'm talking about. We can have what we call the smooth and rough properties of the data. All right, smooth properties, example is location. Are you okay? Talking about the spread, interquartile range. I think you realize that what I'm talking about is statistics purely. We can talk about shape, which is histograms and box plots. Okay, these are all smooth properties. Then the rough properties will be the outliers, the points which are really at the extreme ends. Okay, values more than a certain distance above or below the upper or lower quarter of the distribution. This is just purely, you know, statistics. But the focus of ESDA is able to find a relationship between the map and then the statistics, which is also graphically and visually detected. Is that okay? All right. So we can talk about spatial trends. Spatial autocorrelation becomes one of the smooth properties for ESDA. And then the rough values are different. Obviously, we talk about the rough values again. Spatial outliers, individual attribute values that are very different in magnitude from the neighboring values. I think that is, we need to know this. Okay. Yeah, so we can actually do that for 2 variables instead of 1 variable. Yeah, we can do that. So if you have 2 variables, scatter plots can be used. You can try this in Excel and then do a scatter plot for yourself. You can have 2 sets of data, and then you plot them. Okay, and then you know, you can actually draw a line of best fit and all that. Is that okay? All right. So if you understand your statistics, we wouldn't have to go over this again. Otherwise, it will sound more like I'm teaching statistics, which I don't think I'm ready to do that. Okay. Now, it's important for us to know that when we use the word global, then we are looking at all of the cases, looking at all the, you know, observations within the area of interest, or we can do the local statistics. So we can have global statistics and we can have local statistics. And so the local statistics, you look at just a small subset of the larger set of data. Are you okay? And then we can just look at just if we can window in and then check what is the average of this group of points, so we could do that as well. Okay, so I think most of these are quite statistical. Let's look at this one here. We have a certain graph that will help us to even understand it more. We have the map on the right hand side, and then we have on the left, you have what we call the box plot, and the box plot is actually made up of like the upper quartile, lower quartile, the mean, and all that is actually captured within this. Okay, we need to understand how the box plot works. So please, as an assignment, go and read about it. If you already know it, that's fine. The box, what is a box plot? What is it made up of? What are the values, statistical values that go into that? Okay, I believe you are all on the e-learning platform. So I can actually post this assignment on this graphical display on the left hand side here. I want you to go and look at it. How is it drawn? How do you draw a box plot? Go and look at it. Okay, now, but the interesting thing is that we can actually click on the left hand side and then see it on the map. Okay, where do we have the lower quartile values? Are you okay? Most of the time, people talk about statistics. Ghana is this, Ghana is that, the average one. We don't know where they are even talking about. So that is the solution that ESDA provides for us. Is that okay? All right, so we can actually talk more and more on that. Are you okay? And yeah, it's all going to be just statistics. Existence of general increase in heart disease incidence from Southern Carolina. So it's just data analysis. Please, let's read about it. There's no need to really go over and over again. Yeah, over something that we can easily read and understand. Okay. All right. So spatially lacked box plots, blah 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 blah. All these things are worth reading. Please go read through it. Is that okay? All right. So we even touch on spatial autocorrelation and how they relate to the scatter plots. Is that okay? Yep. Detecting spatial outliers. Okay, I think these are all stuff that you can read and understand. Are you okay? All right. So the stream values in terms of attribute values in adjacent spatial. I think these are all not worth overemphasizing. Is that okay? All right. So guys, read about the rest, and I think we will just continue. But I think for now, maybe we can just ask a few questions. If you don't have any questions, we'll probably end it here, and then we continue another time. Okay, I think we have just 10 minutes. So if you have a question, just go ahead and ask. So one topic that we tagged on two topics today. We tagged on spatial autocorrelation measures, okay, which is actually made up of what? The use of two formulas, Moran's I and Jerry C formulas, which actually calculate the degree of dependence between observations. Are you okay? All right. They simply make use of the coordinate values, the x coordinate value, a weight, okay, which should actually reflect the intensity between the observations. And typically these weights are distances between the points. An inverse relationship exists. So W equal to 1 over D. Okay. So Wij is actually equal to 1 over Dij. All right. And we also just touched on exploratory data analysis, and we said exploratory data analysis actually can be extended to exploratory spatial data analysis. And in the sense that exploratory data analysis touches on, hypothesis formulation, model, okay, actually creating line of best fits, okay, for data sets in our bit to, find a trend, okay, within a set of data sets. And yet we want to be able to relate it to the ground. So there should be a way to link between what we see on the map and then statistical values. Okay, so this is what today we are talking about. And we need to appreciate all the various aspects of statistics that relate to, you know, calculating the shape of a distribution. Are you okay? All right. We want to talk about the smooth parts of the data. Are you okay? The gradients. Are you okay? The rough part, the outliers of data. We need to understand the various components. But the key thing in GIS is that how do we relate it to what is going on? So the map, the linkage between the map and then the statistical data. That is what our focus is on under exploratory spatial data analysis. The idea is to find pattern within data. In fact, at the end, we should be able to even do a prediction, because if you can have a line of best fit, then you can also predict. Are you okay? Because then you have a certain relationship of formula. Y equal to mx plus c is an example. We can use it to fit that into a set of data if you know that relationship exists. So the outliers, we need to know the key terms. Are you with me? All right. Spatial autocorrelation itself is actually the smooth property when we are actually doing exploratory spatial data analysis. Are you okay? Because spatial autocorrelation, remember, it actually tried to tell us whether there's a relationship between observations which are neighboring observations. Are you okay? All right. So let's be able to distinguish between, the various, aspects of statistics as it relates to data analysis. When someone gives you data, can you do some correlation? Are you okay? Which we are actually calling spatial autocorrelation. All right. So please ask 1 or 2 questions, because some of these things, unless someone asks a question, it becomes, quite monotonous. Are you okay? Yeah. Any question? Otherwise, I think we are ending the lecture. I think I want us to end it and then to be continued another time. Okay, that's fine. So guys, thank you so much for availing yourselves, and see you same time next week. We need to move at a certain speed, so please try and be available. Let me double check the attendance. What I have done, if you don't hear your name, it means you are not around. Is that okay? So pay attention. Nana Bonsu, Muhammad, Yakubu, Ibrahim, Akwete, Enes Nyaku, Cyril Tete. So these are the names I have. Yes.
Samuel Latte is here. He's at my premise. He's here. He's fully.
Samuel Latte is with you. Okay. All right.
I'm around. Say
okay.
Benizata.
Yes. Okay.
Sir, I'm around.
Okay. Peter Mpunsem too, you are around. Okay. All right.
Abdul Martin Abubakari. I'm around, sir.
All right. Okay, that's fine. All right. What about Joshua? Joshua Tete. Joshua, have you heard of him?
He's a technical person.
Have you heard of Joshua? Okay. All right, guys. So let's okay. So let's end it here. Okay.
Hello, sir.
Yes.
Hello, sir.
Yes.
Sir, I'm coming to Accra. I'll come and visit you.
Okay.
Hello, sir.
Okay. Yeah, Joshua. Is Joshua around?
Yeah, I'm around. Yes, sir, I'm around.
Joshua. Okay.
I'm also around.
All right. Okay. Please come and visit me. Okay.
Okay, sir.
So everybody's around. Everybody's around.
Everybody's around. That's
Unless you stay at Magina.
Okay. All right. I'll get to you. Okay. All right, guys. So take care. Enjoy the weekend. Okay.
Okay, sir.
All right. Bye-bye.